our next topic is to add to that knowledge is to learn a little bit more about benefits of wetlands. And Amanda Sweetman, is that right? Should know, we emailed enough, is from Utah State, and I'm going to just let her give you a little bit her bio. And she had the opportunity, I believe, to teach Wetlands 101 this last year, yes, at Utah State. And so I had to twist her arm a little, but got her here to teach us. I told her to be gentle.
We won't get too technical, just a little bit.
Do you want to hold the mic or?
I really don't need it.
Okay.
Can you guys all hear me if I
I'll
talk up?
just put it right here.
Yeah? Oh, you need the microphone for that. Okay. Sure.
You pull it, see. You pull the trigger to advance the slide.
Is there a laser too?
And there's a laser on the right hand. You should point it at this. There's a laser and you point it at advance here. Should.
Yep. Well, that's a really happy pointer clicker. Okay, so I know Claudia said we were going to talk about the ground, but I'm going to talk about where the ground and the water meet, because that's where wetlands are, right? Wetlands are the interface between land and water. So, and kind of the whole purpose of my talk is to talk about the natural state and how natural it really is, right? And how much we mess with it as inhabitants and people who like to use it. So the objective of my talk is to understand the natural processes and functions of these wetlands and what they do for us, why we should care and why we should try to protect them. So we're going to start out kind of with a little bit of ecology and then talking about ecosystem services. I'll give you some examples from across the country. There are a couple of big ones right now going on, as you guys may have noticed, and then some more local examples, and then we'll talk about potential challenges to the Bear Lake. So here's the littoral zone that Claudia's been talking about. So lakes are split up into multiple zones, but we're going to talk mainly about these two zones, the limnetic zone and the littoral zone. So the littoral zone is where light reaches through the water all the way to the substrate or the ground. In the limnetic zone, you have open water where light only penetrates so far. So here's your euphotic zone, or where light penetrates to. And then below that, you do not get enough light to have things like photosynthesis. So you stop having rooted plants, you stop having algae that photosynthesize, all of those things. So wetlands and the shoreline that we've been talking about are at this interface between terrestrial and deeper open water. So part of the problem with dealing with wetlands, and I deal a lot with wetlands because that's what my master's degree is on, and teaching a class, and a lot of you in the room deal with wetlands too, either the Army Corps of Engineers or whoever you may be on trying to define these zones and areas. So the problem is they're really hard to define. They're very different depending on where you are, and all the different physical characteristics can vary quite a bit. So you can have these smaller areas. So this is an example of a prairie pothole wetland in the Midwest. This is where a huge majority of the breeding migratory birds in the United States are formed. So just because it's little doesn't mean it isn't ecologically important. You can also have immense stretches of wetlands. This is a picture of the Everglades in Florida. It covers miles and miles, and it provides crucial habitat for birds and alligators, and people like to play in it and all of those things. So size is an issue. Other things that are issues are water. Water is very different in a lot of these different places. In the arid West, you have these seasonal wetlands. So this is a playa here, right? So for most of the year, those are dry. is that considered a wetland if it's dry? How do you know? In other areas, like the shoreline of Bear Lake, you have a moving line. When do you know if that's a wetland? So coming to the conclusion of what is a wetland is kind of it's a hard place to start figuring out what you're going to do and what you're going to call a wetland. So when you go through and look at a lot of the different definitions of wetlands throughout all the regulatory agencies, state and federal, three main things come out. That you have to have water, that you have to have a certain kind of plant, and that you have to have soils that are characteristic of places with water. So you have enough water that's present during the year, especially during the growing season, that you have hydrophytes. Hydrophytes are plants that are adapted to living in water. And then you have the development of hydric soils. So these hydric soils have different characteristics than soils, say, in an upland, where they don't have water sitting on them for a certain period of time. So here you can see an example of a wetland up in the the wildlife refuge at the north end of the lake. This is alkali bulrush, which is what I study when I'm not giving talks and teaching classes. So here's a hydrophyte. Here are, below this, your hydric soils that have been sitting in water, and here is your water that's present. But later in the year, that's dry. So if you don't know that your plants are adapted, those plants which persist when the water is down, that those are hydrophytes, you would maybe not know that that was a wetland if you came by it in August. So to talk about these a little more in depth, hydrology, to have a wetland, per the definitions, you need to have an area be inundated for at least 2 weeks during the growing season. So there needs to be surface water or water sitting above the surface for at least 2 weeks. These are the hydric soils I was talking about, right? So here you can see kind of the characteristics that make a hydric soil. You see those red kind of strange looking mottles in the soil? That's where iron has been reduced and oxidized and reduced and oxidized and reduced and oxidized as water goes up and down. So, and what causes that transformation is anaerobic conditions. So when you have water sitting on a piece of land, the bacteria and the plants and anything that's living in the soil uses oxygen for respiration, right? To create energy, you need oxidation. So oxygen is the preferred choice, right? It gives you the most energy per molecule of oxygen. We all use it. That's why we breathe. It's great. Oxygen is great stuff. But when oxygen is depleted, you get anaerobic conditions, so without oxygen. And that creates this reduction because the bacteria in the soil need something to get energy from. So they go down the chain of things that give you the most energy per molecule. And iron is one of the higher energy sources. So remember my example of how would you know if a wetland was a wetland if there was no water and you didn't know what the plants were? You can dig a hole, and if you see these characteristics, you can say, aha, there is a wetland there. It's very tricky. There are examples down in the West Desert where Las Vegas is pulling a lot of water from the aquifer down in southern Utah. Well, so wetlands have been dried up, so they're like, there weren't any wetlands here anyways. 5 years ago, 10 years ago, there weren't any wetlands. We haven't done anything. Wow, that's not really true. You dig a hole and you say, ha ha, no. There were wetlands here. You just drained the water before anyone was looking. So it's an interesting diagnostic, and you can feel it's fun to go and dig a pit and say, ha, I know that there was a wetland here at some point. So and then the last part of that equation for what makes a wetland, the hydrophytic vegetation. So these are defined as macrophytes, or higher plants, anything that's not an algae, that's typically adapted to being inundated, so having its roots wet, or saturated conditions. So it's hard for plants to live in conditions where there's no oxygen. So that requires a certain set of adaptive traits. And you can see that in plants like the alkali bulrush here. They have roots that spread along the water surface so they can get more oxygen. They have larger cells that can move oxygen from the above ground parts where they are out in the open air into the roots so their roots don't die from lack of oxygen. So here's kind of a conceptual diagram that my students got really sick of seeing. But it's how you understand how wetlands all come together and all of the interesting interactions in the natural world and why they're so fragile, right? So you start out with your climate and your basin geomorphology. So Berry Lake, dominated by snowmelt hydrology, right? So that's your climate, but it's very arid in the summertime. Your basin geomorphology allows you to have a water holding space, right? There's a geologic history here where faults happened, earthquakes. I don't remember if you guys remember the one that happened like a year and a half ago. All of that has shaped this landscape, and here you have this wonderful place that holds water. And you have a climate that has enough extra water that it stays in the lake. So here are your two background conditions that you have to have. And these then modify your hydrology, so water level, flow, frequency, all of those things. This map over here, right, that's your hydrograph. This hydrology then goes through and modifies your physiochemical environment. Big long word, but it basically means what are the characteristics of these areas. Are your soils anaerobic? What's your pH? Are there high levels of salt? A lot of wetlands in this region of the world are very saline. If you go out into the wetlands up at the wildlife refuge in August, you'll be walking on an inch of salt because the way the water seeps, you get solids going up, and that also impacts what you can have growing there. So hydrology changes this environment that you get here, which then allows you to have specific biota, right? So if you have standing water, your plants have to be modified or adapted to be able to persist in standing water. Do you have high salt content? Your plants have to be adapted to dealing with things like that. That's very difficult. So all of those things then determine the biota that you get in these regions. A lot of it depends on if we want to be here as humans. So, and then it's important to remember the feedback loop between your animals and plants and humans on things like hydrology and physiochemical environment. And that's what I want you to think about throughout my talk. I know it'll get a little scientific, and hopefully I won't bore you too much, but how much do we alter these things? And how much, where's that balance going to come in with how much we alter the landscape and where it needs to be able to persist and have healthy systems? So hydrology is kind of the most important of these three things in having wetlands that are that persist through time. So as we talk about the lake level rising and falling, you all know and care very much about the hydrology of this area. So without water, you get the drying of your wetlands. And the hydrology is great for other things too. If you get things like sediment buildup here, so as you have water coming off the land, you get sediment building up. You no longer have your harmful materials like nutrients or pollutants being washed out. So you no longer get this import and export of important things in your wetlands. An example for around here, if you don't have water any place, you don't get the plants that then can purify your groundwater that runs into the lake. So all these things are very important and are related to each other. So talking a little bit more about Berry Lake. Berry Lake's very oligotrophic. Anybody have a guess as to what that word is? Say it louder. Sterile? That's close. Okay. Not supportive to life. All right, who else? Okay, lots of mumbling. All right, so an oligotrophic lake, sterile is close. It has very few nutrients. It has very few of the things that promote life. That's why you get the beautiful blue color, right? Not a lot of algae photosynthesizing, making it green in the lake. So as I said earlier, it was formed by geologic activity. There's several faults around here that have shaped this basin. The hydrology is dominated by snowmelt, as we're all seeing. I don't know if you guys have been looking at the SNOTEL website, but there's 117 inches still up at Tony Grove. So we haven't seen the worst of it yet, or the best of it yet, depending on what you want. And it's also used as a reservoir for water storage for the Bear River. So here's kind of two different representations of the lake. And what I was talking about earlier with the littoral zones, think about the distribution of where light reaches in the lake. It's very different from east to west. You have a much larger littoral zone over here where it's so shallow, versus here it's a very narrow band where light reaches to the bottom.
Amanda?
Yes?
Does Tony Grove drain into Bear Lake, or does it go the other way?
I think it actually goes the other way. I think so. But I pay attention to that because there's a betting pool going on at U.S.U. about when Logan River is going to peak. Oh, yes. Get a whole bunch of hydrologists in a room. Everybody's really excited. Oh, geez. So the distribution of where you can have plants coming out and living in the lake are very different. And you get different uses by the fish that live in the lake and the macroinvertebrates that live in the lake and all those things, depending on the kind of environment that you have and the depths that you have. Who can tell me where the best fish spawning is? Yeah, so why is that? It's deep, it's rocky. There's a different environment over there that allows you to have that biomass production over there. So this kind of leads us into my next point. Why should we care about them? What on earth do they do for us besides kind of smell bad and produce biting mosquitoes? And, you know, a lot of people don't like wetlands. In the West, they don't smell as bad as in the East, let me tell you. But you really should care about wetlands, at least in my point of view, since I study them and devote all my time to them. They're wildly productive systems. They rank up there with the tropical forests in terms of ability to produce things. So not only do they produce biomass or plant life and animals, they also provide functions and services that we all use. So the first one I'm going to talk about is habitat and biomass production, right? So I talk about it like a scientist, but really what I'm saying is it grows a lot of stuff. You get a lot of fish, you get a lot of bugs, you get a lot of plants, and all of these things support the food web. And a lot of wetlands support the bottom of the food web, which is exceedingly important to the success of our higher trophic levels, which are the things that we like to fish for and hunt and all of those things, because you get plants that grow in wetlands. You also get them as spawning grounds. About 95% of the fish that we catch in the United States depends on wetlands. 80% of the birds that we hunt in this country are wetland dependent, either for resting grounds on their way to where they want to nest, or as we see every day at the Wildlife Refuge and down at the Bear River Migratory Bird Refuge, they nest here. There's a lot of production of those birds. And then on the other side of this is that 50% of the endangered species in this country are wetland dependent at some point in their life cycle. So it's really very crucial that we preserve these areas. Unfortunately, it's where we all like to live, too, you know? Everyone wants to live near water. Just kind of an interesting side note that I'm sure you guys all know, but I got geeked out when I was doing more research for my talk, was the 4 endemic species of fish that you have in the lake. Lakes are often biodiversity hotspots, especially a lake this old. You guys may have heard of all the cichlid fishes over in the African Rift Lakes, where you've had massive biodiversity explosions of really cool fish and evolution happening at very small timescales. So these areas are really neat. So another one that's more important for humans is water quality improvement. So wetlands have been likened to sponges, or kind of like the liver of the landscape. And this is because they kind of act like sponges. Wetlands are at this interface between the land and the water. So ground runoff comes across the land, picks up sediments and mud and gets all gross looking. If it comes off of your fields, it picks up your fertilizer, so a lot of nutrients like nitrogen and phosphorus. It picks up heavy metals, it picks up other pollutants, it picks up trash, all of that stuff that we don't really want in our water, right? We like that Bear Lake is brilliant and blue. So the water comes off the land with all of these things in it, and it slows down when it hits the wetland because it's this broad open area with plants and other things to catch it and kind of trip it up. So the velocity of the river slows way down, or the runoff slows way down. So when you have something fast hitting something slow, you get a change in the dynamics of the system, and what happens is that you get sediment falling out of the water column. So wetlands trap sediments, which is great. It not only clears up your water, it also builds land. You have, in these wildly productive systems, you get plants growing, so they take up these minerals and things like carbon, which we all care about now that global warming is such a big problem, right? So it traps these minerals, the plants grow, they die, they get buried, and you've trapped this mineral in this system. In other parts of the world where you have peat accumulation, so biomass that grows and then gets buried, you have a massive carbon sink. The world is covered by about 9% of the world's surface, land surface, is wetland. About 14% of the world's carbon is stored in those wetlands. So they have a disproportionate effect on your carbon storage and things like that. So another way that wetlands clean water is that they transform chemicals. So remember when I was talking about anaerobic conditions, that you have less oxygen, bacteria need some way to get energy. What are they going to do? They're going to grab on to nitrogen, because it gives you a lot of energy when you break that down. So, which is great for those of us who don't want a lot of nutrients in, say, Bear Lake, right? So you get anaerobic conditions, you get these bacteria changing nitrogen, and a lot of it is released and is denitrified. So you get rid of some of these nutrients, which is great, because if all the nutrients from all of our fields ran into the lake, you'd go from an oligotrophic, sterile system to a eutrophic system. And so if oligotrophic is sterile, eutrophic is the other end of the system. If any of you have been back east, lakes back east are not brilliant and blue. They're green, they're kind of dark, no one really likes walking in them because they're slimy and ugh. You don't want that to happen here. So it's great that you have wetlands that can clean this water for you. So all of these characteristics are kind of why we as humans use them as wastewater treatment, right? Logan has a huge area devoted to wetlands to clean the water. So people have known this for a long time, and they use them in different aspects, but it'd be great if we could increase people's knowledge on this and increase the usage of wetlands. So one thing to think about with Bear Lake is how long water stays in the lake. So the average residence time for water in the lake is about 37 years. So water comes into the lake from somewhere, off the mountains, from a spring, wherever it is, it stays in the lake for about 37 years. So this is kind of an intermediate time zone. I mean, some lakes hold water for thousands of years. Some hold water for a year, maybe. But 37 years is kind of a long time, and it makes it sensitive to things like nutrient loading. You get water that's holding nutrients in the lake, it's there for 37 years. That's a big deal. That's longer than I've been alive. Seems like a big deal to me. And this nutrient load that I'm talking about and worried about is mostly from the river. So about 60 to 80% of the phosphorus that you find in the lake is from the river. This is just one of the ways that the connection between the river and the lake has altered the lake. So we don't want phosphorus and nitrogen in the lake. Currently, algae is limited by those nutrients. If you get more of them, you get more algae, you get greener waters. You can have toxic algae, which makes it so that you can't swim in the lake, it would drastically change how we would use the lake. So all of these things are important, but really, why are you all here? Why does everyone build houses here? It's because living on the lake is great, right? It's for recreation. So this is just another one of the ecosystem services that I'm talking about, right? Recreation, hunting, fishing, all these great things. I come here as often as I can in the summer to play in the water. It's a wonderful place, especially in this arid place in which we live. So that's why I think a lot of you are here. So now let's go into kind of a more tangible example of ecosystem services that wetlands can provide. And this isn't here, and it's not specifically related to Bear Lake, but I just wanted to bring it up as a reason why these are important. So if any of you have been listening to the news, you know that the Mississippi River is really high right now, right? Historic levels not seen since 1927. And this is going to cost billions of dollars. It's going to have impacted farmland. It'll have taken people out of their homes. And why? You know, don't we have a system of levees built to protect these areas? Hundreds and hundreds of miles of levees. And so you say, okay, they've built levees. We should be fine. We should be protected. Well, they blew out a 2-mile section of a levee in Illinois to protect some of the towns that were down below it. Why would they have done that? Anybody been paying attention to the news and know why? Come on. Refineries on the coast? So you're protecting the refineries by not letting the flood get too big. Okay? So, but why does blowing a hole in the levee protect it?
Well, it dissipates the force of the water.
Exactly. Exactly. So this 2-mile hole in the levee dissipated water over 130,000 acres of water, or of land. So this is a picture of after it happened. So here's the little town. Here's, the water is spread out over this big area. So, and that's dissipated the force of the water. So before humans came in, European settlement came in and destroyed a lot of the wetlands and created these long, straight areas where we could push boats through and transport things that we wanted to transport up and down, because water is a great way to do that if you don't have things like automobiles. So we came in and took out all the beaver dams. There were like 60 to 100 million beavers in the United States before European settlement came in. Part of the reason they were destroyed was because everybody really liked hats made out of beaver, but a lot of the reason was because nobody wanted to have to take their canoe out of the water, walk it around, and put it back in. It was much more convenient to have a straight waterway. So you start making straight waterways, you have water that goes much faster, right? If you guys have paid attention to what happens when you constrict water, it goes faster and it gets higher. So flooding became a big issue when this started to happen. So they built levees because, well, water's coming at you, build a wall. Great idea. Of course, what does this do but exacerbate the problem of making the water faster and higher? So now when we have a wet year, you get this. And it's starting to happen more and more frequently, right? So there's, in the news and in the literature, if you're a scientist and you pay attention, there's this huge hullabaloo about leaving levees broken. They're not going to fix this. That's a big deal. That's somebody's farm. That's several somebody's farms. And they want to do this all along the river because they need to replace the 35 million acres of wetlands that have been destroyed. 35 million acres is about the size of Illinois. So that's the state of Illinois. So all those wetlands that used to occur along the river have been destroyed. So before we destroyed those wetlands, the sponge that is the wetlands along the river held about 60 days of flow. So it dissipated a lot of water and held water in places. Now it holds about 12. So as the gentleman in the back said, you have a lot of destruction. The refineries on the coast, all of these things are in danger because this water gets going so fast. And then not only do you have riparian wetlands, right? Wetlands around the river, you also have floodplains. So floodplains have been disconnected. So New Orleans sits right on the Mississippi River historic floodplain. So what they've done instead to protect those refineries is kick it around into the Atchafalaya River. So all that water is going to come out here instead, which is fine. It's actually going to do great things for those wetlands. It's going to build land. It's going to put nutrients into those areas which have been disconnected from this flow for a long time. It's also going to displace a lot of people, but it can be a good thing because floodplains dissipate force of water. So a closer example to home, you guys probably all remember the late 80s, the floods in the late 80s, right? Down in Salt Lake. So we've disconnected the Bear River from its floodplain. This is historically the floodplain for the Bear River. So this is now the Bear River Migratory Bird Refuge, right? So we've put it into a whole bunch of nice little boxes, and we can control how much water goes through where. Well, that's great, except for when you have a year like this year. So last time we had as much snow as we have this year was this year, when they sent water right down State Street in Salt Lake City. So instead of having wetlands to dissipate the force of the water, here you have a straight and narrow area where water goes faster and gets higher. It's really destructive too, right? So here's the floodplain. This is the old headquarters at the refuge underwater in the late 80s. I don't know if any of you went and visited it pre and post the flood, but it was utterly destroyed. So water's a powerful thing, and wetlands are a great way to decrease some of that power, and that provide all kinds of other services. So a quick example of someplace else in the world, the Army Corps of Engineers in Massachusetts did a whole long study on what they were going to do to protect a town on the Charles River. And so they decided, instead of building levees, that they were going to purchase a whole bunch of land. And so it cost about $8 million to purchase this land, to be a floodplain, to be a riparian wetland, to hold this water. It would have been about $17 million a year to put in flood control structures. So $8 million one-time cost to buy land, $17 million a year to put in levees and dams and all of those things. It also gives really great benefits on top of that. About 200 jobs are supported by this project. And it's a place where people recreate and go in canoe, and birds live there and all of those things. So wetlands are really a good deal. I'm just waiting for everybody else to realize it. So in terms of Bear Lake and the wetlands here, what are kind of some of the challenges that it faces? Well, you have climate trends that are getting kind of out of whack, right? So in the last 45 years, I think there's been 25 ice-free years. 11 of those have been in the last 11 years, 7 of those have been, I'm getting this all mixed up. Anyways, the frequency of ice-free years is increasing. So climate is changing, whether we're ready to accept it or not. Drought, as we heard earlier, using the reservoir, the lake as a reservoir exacerbates drought. Even though we're getting a whole bunch of water this year, doesn't guarantee that we're actually out of the drought. And then other things include invasive species, so Phragmites, which we all hear so much about, the quag mussel, the zebra mussel, all kinds of other problems are facing the lake and endangering those services that we've come to expect and that we rely on. So coming back to the point I asked you to remember at the beginning, how natural is this lake, and where is that balance going to come in with what we want and depend on from the lake and what the lake needs to continue to function? So, thank you. Questions? That was a study that came out of U.S.U. about 10 years ago. You'd really want to talk to Wayne Wurtzbaugh about that. I'm not a hydrologist, sorry.
We have the main source, the Bear River, coming in, but around the lake we have natural springs running in.
Mm-hmm.
We have irrigation water that runs in. On the natural springs, what would be the effect of ATVs going through these springs as the water runs down to the lake?
Springs are a pretty fragile system. I don't know for sure. I've never looked at the literature on what the potential impacts of ATVs might be on springs. But they're easy to clog up. They're very easy to damage and destroy. Driving over one could be catastrophic, or it could mean nothing. It depends on the strength of the stream. It depends on the strength of the water coming up out of it.
Well, not where the source comes in.
Mm-hmm.
Let's say the spring is up on the side hill, and then the water flows down into the lake. And when the lake is down, you still have that spring water coming down in vegetation.
Mm-hmm.
And you have lots of traffic going through there, through that water.
Wetlands are fragile systems. Walking in wetlands can damage them. I know this from personal experience. Walking in the alkali bulrush flats, like I did several summers in a row, I could tell where I'd been. And I'm sure I could go back and still tell where I had been, because I walked there every other week, and you damage them. You damage their roots, you damage these systems, and wetlands in particular, hydric soils are kind of spongy. You get a lot of organic material in those areas. So compaction on wetlands can be devastating and can completely change your vegetation, how water flows over it, all of those things. Compaction is a really big deal. And when you're doing a restoration project, this is kind of my knowledge that I could give you, is that if you have trucks bringing in things and you have bulldozers coming in and you're trying to do a restoration, you have to be exceedingly careful where you drive, and you have to rip it up after you leave. You basically paint yourself out. You go in with a big heavy piece of machinery, you rip your way out so you haven't compacted that land, because when you compact areas, you get things like swales and you get water collecting there, but plants can't grow there because the roots can't go through the compacted ground. So I would say the ATVs driving over an area could be devastating, or it just a lot depends on the soil. It's hard to say without going out and saying, okay, here's a spring that no one drives over, and here's a spring that somebody does drive over.
I guess my main question is, if we didn't have ATVs down on the land that's now exposed and assuming in the water, driving around the lake, would that be better for the ecosystem than allowing them down there? That's kind of a loaded question.
I'm trying to get around answering it, if you couldn't tell. Yeah. I mean, it's kind of an obvious answer, right? You have things driving on plants. What happens to those plants?
Right.
Can I respond?
Yes, please.
We were talking about that at lunch, and our neighbors apparently over the winter have disked or harrowed the beach area by our properties, and I remember very clearly in the first few years of the drought that as the beach was exposed, it was hard as a rock. It was like pavement by the middle of the summer. But as the ATV traffic began to take off, it just changed the entire surface area of the beach, and it became much softer. And that's when the invasive plants started coming in, because now they can take root. And it just took off. So we likened it. It was exactly the same effect as harrowing, plowing and harrowing a field. That stuff grows a lot better than it does on that sun-baked, untouched, unbroken surface.
It's interesting, if you look at the historic Bear Lake area, prior to white man's arrival, the landscape was quite different. But when the Mormon pioneers came in, they built canals basically from every spring that goes around the lake, starting Big Spring, Swan Creek, Fish Haven, St. Charles, all the way around. Those have run for well over 100 years, and they've created a lot of wetlands that were not here prior to Europeans' arrival. What's what's your opinion? We always talk about loss of wetlands, but we as humans also create a lot of wetlands through irrigation. What's your opinion?
We don't create that many wetlands. In terms of the mass balance in the country, we don't create that many wetlands. Okay. Well, so answer me this. Those wetlands get a lot of runoff from the fields, which I'm assuming people fertilize. Yes? Nod your head, yes. Fertilize. And cows. So anytime I was out in the wetlands, they were full of cows. I was like, what is going on with all the cows? So yes, we create these wetlands, but these wetlands are then connected sources to the lake that get these impacts from our use of the land. Fertilizer, another natural type of fertilizer, disturbance, all of those things. So yeah, it's great that we've created some wetlands, but they're pretty small. And some of them are healthy and some of them aren't.
Is this shoreline truly a wetland where it was lake bottom? By allowing the lake to go down, isn't it a fake wetland?
It's still an interface.
Is it going to make the lake dirty when it comes up because of all those plants that have grown?
It won't make it dirty. There will be a change. I mean, you have successional change in any ecosystem, right? So naturally, you could have things like the lake level rose. It reached the point at which it is no longer contained in the valley and it would flood out, right? This happened with Lake Bonneville. So that would be a successional change, right? You'd have vegetation in one place. So way up high, you'd have wetland plants along what was used to be the edge of the lake. It had this catastrophic flood, drained out. Then you have these plants way up high that no longer have a source to water. 2, 5, 10 years goes by, depending on the type of plant. If it's a tree, it'll last longer. If it's not, if it's a little herbaceous thing, it won't last very long. You get changes in what you have growing along these areas. So along the lake, you'll have a lot of trees that are up to their noses in water. This will cause die-off. A lot of trees are not hydrophytes, like I talked about in my lecture, right? They're not adapted to having their roots be flooded. Unfortunately, the Phragmites problem, not probably so lucky because they're connected by rhizomes, right? So yes, you might have a stand that gets flooded out, that's in the lake, gets covered up by how many feet of water was it going to be, like 11 something? Okay, so 11 feet of water. You'll cover over a couple of stands of Phragmites. The great and horrible thing about Phragmites is that it can travel long distances by runners. So these connected stands have a much greater chance of persisting.
This is really a follow-up to the last question. Because I think what the question is, if the lake comes up 11 feet and now is this, suddenly we flooded this huge area of vegetation, I mean vast, you're talking about 9-point-some square miles of land which is now vegetated heavily. And suddenly we have all this biomass.
Okay, I get what you're trying to say. I would say you'll have a couple of years of walking on stuff you don't want to walk on. It'll be organic soils, right? You'll have organic soils that have accumulated in these areas, and it'll have to get rinsed out. Yeah.
Isn't it better to keep the lake level at a level so you're not constantly...
Yes and no. Yeah. Yes and no. I think you need some fluctuation. To have a healthy system, you need some fluctuation because you need these changes. You need the hydrology to change. You need cycling of nutrients. I mean, it'll be good. It'll change the way the system works. So wetlands are dynamic systems. Change can be good. Holding things steady too long can be unhealthy for a system as dynamic as a lot of these systems are.
So what's the best thing to do during drought years where the water leaves the wetland? Do we just allow the vegetation to grow and come back naturally, and then as the water comes in, accept that that's part of the natural fluctuation of this area and accept a boggy vegetative beach, or just go to Hawaii?
Go to Lake Michigan, it's great. Another oligotrophic system was sand. That's a hard one. I think it depends on what the vegetation is. If it's Phragmites coming in, take it out as quickly as you can. Because even if the water comes back, you won't have a beach ever again. You'll just have a Phragmites stand. If it's the low-lying sedges that come in naturally and are what the majority of the vegetation is around here, I wouldn't worry about it too much. They don't deposit that much biomass anyways. Wear sandals, wear chacos. That's what I do.
They say if you cut the Phragmites under the water, that they won't come back. They have to be drowned. But if they're sticking up above, they're going to be alive.
Yeah, I'm not the, yeah, you say people are going to. Weeds aren't really necessarily my specialty. I specialize in native plants. So, yeah, great. All right, well, thank you.